Hi everyone, welcome back to your course Chemistry for Engineers. Today we will be talking about the fourth topic of your module number 1. Again, this is your instructor, Engineer Janaika A. Tapiador. So far, the three topics that we have covered for this course are your overview, energy loss, and electrochemical energy. Today, we deal with nuclear chemistry and nuclear energy. So as you can see, we actually have a few topics for this particular topic, nuclear chemistry. So medyo madami po siya, but I hope that this video will be able then to help you understand how this actually happens. So let me first start with the introduction. So it says here, ultimately, the chemical energy that fuels life on Earth comes from sunlight. So all the chemical energy that our Earth uses actually comes from sun. So that's our main source of chemical energy. Our plants, they actually convert the radiant energy from the sun into chemical energy through a process which we all know we call photosynthesis. And as a byproduct of those photosynthesis, we have your oxygen and carbohydrates. Basically, all life on Earth could not exist without energy from the sun. But have you ever wondered where the sun gets its energy? So you actually know as well that our sun is a star. So all stars actually use chemical or nuclear reactions rather that involves changes in the atomic nuclei to generate their energy. So the energy that is being produced by nuclear reactions, which happens in the sun, is actually the reason why it produces a lot of energy. So for example, the sun produces energy by fusing hydrogen atoms to form your helium, and in the process of fusing those two hydrogen atoms and in the production of your helium element, it releases a very large amount of energy. The fusion of your hydrogen to form helium is the dominant nuclear reaction for most of a star's life. So imagine you have two atoms of hydrogen, and those two atoms hydrogen will actually fuse together in a process we call your nuclear fusion. And when those two atoms of hydrogen fuses, a vast amount of energy is being released. That's why we can actually harness those particular energy, and that's what fuels life not only on Earth but also for other planets as well. So the energy coming from the sun is our main source of chemical energy. However, at the end of a sun's life, of course, we all know that things come to an end. It says here, toward the end of its life, the hydrogen in the star's core is exhausted, and the helium atoms fuse to form more progressively heavier elements. So when all of the hydrogen in the sun is already used up, the helium atoms now will actually fuse together to create higher elements or higher atomic number of elements or heavier elements. So it also says here, a select few stars end their lives in a dramatic supernova explosions. I believe you have already heard this particular term, supernova. So this is a, it's like just an imagination of what happens when when a supernova occurs. So as you can see, it's actually a very pretty picture. And the nuclear reactions that occur when a star goes supernova are responsible for the existence of all naturally occurring elements heavier than nickel. I believe this is actually one of the reasons why there's what we call your Big Bang Theory. Diba? It entails that our Earth, the Earth or the solar system was formed from a supernova explosion. So from that explosion, a lot of nuclear reactions occurred, forming elements, heavier elements, starting from, as you can see here, nickel. And thereby, through time, it actually formed our planets. So we have been talking about nuclear reactions. But what is actually involved in the nuclear reactions is the nucleus. But we cannot deal with the nucleus without understanding how the atom works first. So in this particular subsection of our topic, we will talk about the atom and the nucleus. Although I believe you already have a background on what an atom is, however, let's just recall what you have already learned in your high school courses. So let's start first with the atom. So as you all know, the atom is the smallest unit of matter that is composed of your three subatomic particles, namely your proton, your neutron, and your electron. Excuse me. An atom consists of a positively charged nucleus surrounded by one or more negatively charged particles called electrons. So, kumbaga, parang nasa gitna, kunyari, this is the nucleus, and surrounding the nucleus are your electrons. The positive charges equals the negative charges, so the atom has no overall charge. It is electrically neutral. So, as you can see here, we have a table which contains the charge and the mass of the three subatomic particles. Of course, you have your electron, and as we have been already dealing with your nuclear, or rather your electrochemical energy, you know that an electron has a negative charge. And as you can see here, its mass in terms of the atomic mass unit is 0.000549 or 0.00055 atomic mass unit. And inside the nucleus are your protons and neutrons. Now, your proton is actually a positively charged particle having a mass of 1.00782 atomic mass unit. And finally, you have your neutrons with a charge of 0, having a mass of 1.00867 atomic mass unit. So as you can see, the negative here will actually counteract the positive here. Therefore, it conforms with the statement earlier which says that the atom has no overall charge. So again, the atom contains three subatomic particles, your electron, your protons, and your neutrons. So it says here, the atomic mass unit, or we abbreviate it as your AMU, is defined as exactly 1/12 the mass of a carbon atom that has 6 protons and 6 neutrons in its nucleus. The atomic mass unit is a unit which is based on your carbon atom. It's based on a carbon atom because typically almost all the things that we have on Earth is made up of carbon. Now, one thing that you have to take note of is your Avogadro's number. So that's 6.022 times 10 raised to 23 atomic mass unit in 1 mole. Now, what does it mean? It means that for every mole of an element, there are 6.022 times 10 raised to the raised to the 23rd entities. Kumbaga, ganun po kadami, parang you can think of it this way. Diba when you say a dozen, you already know that it contains 12 pieces. Parang ganito din siya. So when you say 1 mole, it contains 6.022 times 10 raised to 23 pieces of that element. Parang ganun po yung kanyang interpretation. Now, this particular constant is actually known as your Avogadro's number, which is abbreviated as the capital letter A, or sometimes in other books or references, it's actually abbreviated as N sub A. So, may A po doon na capital. That's your Avogadro's number. And later on, you get to appreciate how it is being used in the calculation of energy when we are already talking about nuclear chemistry. Now that you already recalled what an atom is, let's go deeper to the atom. You have your nucleus. So as I have already told you earlier, diba, you have your nucleus, which is in the middle, and that particular nucleus is surrounded by your electrons. Now we will be dealing with what is inside that particular nucleus, which is the main topic for your nuclear chemistry. The nucleus. So it says here, the chemical changes, which we refer to as the transformation of one form of matter into another, we have studied thus far have only involved the electrons. Diba, when we have already talked about your electrochemical energy, it only happens mainly because of the transfer or the flow of electrons. So that is your electrochemical energy. Now, if we go deeper into the atom, which is now your nucleus, that is what we call your nuclear energy. So it says here, when we discussed these changes in atoms during reaction, we focused on the changes in the electronic structure of the atom. So electrochemical energy deals with electrons, nuclear energy deals with the nucleus of the atom. A little bit background on your nuclear chemistry. So it says here, there is a branch of chemistry called your nuclear chemistry that consider the changes and differences in the atomic nuclei. So this branch is actually the borderline between your physics and chemistry, which began with the discovery of your French physicist named Antoine Becquerel. And because of this, the importance of nuclear chemistry has been really, kumbaga para siyang mas na-amplify. The importance of nuclear chemistry was amplified during the past 100 years because of the discovery of Antoine Becquerel of radioactivity. So, na-discover niya paano ba nangyayari yung radioactivity. It is because of the nucleus of your atom. Now, the nucleus of an atom is composed of protons and neutrons. So, inside, di ba, kung ito yung ulit, yung inyong nucleus, it is surrounded by electrons. And knowing that the electrons is outside, ano po yung nasa loob? So, yung nasa loob, yung natira lang po, which is your protons and neutrons. And these protons and neutrons are collectively known to be your nucleons. So when I say nucleons, I'm pertaining to protons and neutrons. So when we deal with nuclear reactions, it is important that you know how to interpret the symbols of the chemical reaction. So as you can see here, you have capital letter A, you have your capital letter Z, and you have your capital letter X. Now what does these letters mean? The atomic number of protons is actually called the number of protons rather. The number of protons is called the atomic number Z. So that is written below. So just like here, diba? This is an example. Your element is X, which is in this case thorium. And if you take a look at your periodic table, thorium has an atomic number of 90. The atomic number is actually equal to the number of protons of that element. And how about letter A? So letter A here, in our example, is 234, which is actually the mass number. Now, what does the mass number tell you? The mass number is actually the sum of the number of protons and neutrons in your particular element. So your nucleons is the mass number, your protons is the atomic number. Such that, kunyari, tinanong ko kayo, if you take a look at this, how many protons does thorium have? Okay. You should already know that the atomic number is the mass of protons, so that will be 90. And if I tell you how many, or if I ask you how many nucleons does a thorium have, you look at the mass number, and that's gonna be 234. Such that, if I ask you how many neutrons thus a thorium-234 have. So it's simply 234 minus 90, which is, I'm not very good in arithmetic, but that's around siguro 146. Oh, you do the math. I'm not very good with arithmetic. So if I'm correct, okay, the number of protons that a thorium element is 90, and the number of nucleons is 234. Therefore, the number of neutrons is 146. Tama ba ako? Hindi siya 146. Oh, anyway, let me just use my calculator just to be sure. Nakakaya naman sa inyo. So, 234 minus 90. Oh, 144. I'm so sorry. So, not very good with adding and subtracting. So, 144 neutrons. So, if you have your periodic table of elements, anyway, usually this you can download naman na from the internet. So, no need to buy. Pang ano lang yun. So, if you take a look at this, diba, let's go to thorium. Diba? Ganyan siya buo. So, starting from your hydrogen, and then your helium, your lithium, beryllium, boron, etc. etc. So, in this, you can see thorium here. Nandito po siya sa dulo. Such that, let me go to the next slide. Ayun, thorium. That's the element number, or the atomic number rather, which is 90, which you already know to be the number of protons. And as you can see here, this is the mass number. However, pag nakita nyo dito, it's 232. Pero dun sa example natin, it's 234. Because ganito siya. Parang your thorium, madaming, kumbaga, akala, the main notion kasi is, when we talk about thorium, there's only one thorium. However, that's incorrect. There are a lot of thoriums. And one thorium is very different from another. Kumbaga, para siyang, if you talk about dogs, for example, you know that there's a dog, but there are different kinds of dogs. Diba? Meron kayong German Shepherd, meron kayong Siberian Husky, Chihuahua, and so forth and so forth. Kumbaga, parang ang dami-dami niyang klase. Parang ganun din po yung ating mga elements. So, when I say thorium, madami pong klase ng thorium. Mas madali na lang po kasi siya, kasi may numbering na siya. Just like the previous example that we have, diba to? This one. This is called your thorium-234. Meron ding thorium-232. Meron ding thorium-231, and so on and so forth. And, let me check kung ito na siya. So, and these different types of thorium, parang we collectively know it as your isotopes. And this is what we have on this slide. Pero dito kasi yung example natin is hydrogen. So, atoms with the same atomic number but different mass number are called your isotopes. So, we have here an example, your hydrogen. And if we go back, di ba yung hydrogen nyo, ayan lang siya. Oh. Hydrogen. Atomic number is 1, and you have the mass number to be equal to around 1.0078. Yan po yung parang average kasi siya ng lahat ng mass number ng nag-exist na hydrogen sa buong mundo. Para siyang ganun. Average siya. So, atoms with the same atomic number but different mass number are called your isotopes. So, we have an example here. There actually exist 3 isotopes of hydrogen. So, para tayong may 3 hydrogen sa mundo. Parang ganun yung ibig niyang sabihin. You have here your protium, which is a hydrogen which consists of one proton and one electron only. And you have your deuterium, which actually has one proton, one electron, and one neutron. And you also have your tritium, which consists of one proton, one electron, and two neutrons. Sometimes we refer to this as hydrogen 1, hydrogen 2, hydrogen 3. So as you can see, dapat may 1 pa dito eh. Kasi diba, this is your element, this is the mass number, and below is the atomic number. Pero hindi na nilagay atomic number dito. Such that you have your hydrogen with a mass number of 1, hydrogen with a mass number of 2, and hydrogen is the mass of a mass number equal to 3. These are called your isotopes of hydrogen. So, parang meron din siyang isotopes of carbon, isotopes of your thorium. So, different types of parang same element, different types. Parang ganun po yung kanyang ibig sabihin. So, when we are talking about a single type of nucleus, the term nuclide is used. Diba? Para siyang ganito. You have 3 types of hydrogen and these are called isotopes. Pero pag ito lang yung, kumbaga ito lang yung dinidescribe ko or ito lang yung pinag-uusapan natin, we term it as your nuclide. So the nuclide hydrogen 1 or the nuclide hydrogen 2 or the nuclide hydrogen 3, parang ganun. Collectively, they are isotopes, and when I talk about one single isotope, it's actually a nuclide. Ganun po. So, furthermore, additional information about your nucleus. The nuclear force is the force of attraction between the nucleons that holds the nucleus together. So, of course, diba, very compact po yung ating nucleus, having that it's in the center of the atom. And there's actually a force that holds the neutrons and the protons together. And that particular force is known as your nuclear force. It says here, the nuclear force is very different from and much stronger than the electrostatic force, that holds negatively charged electrons around the positively charged nucleus. So, kumbaga po, it only says here that your nuclear force is much stronger than your electrostatic force. Obviously, kasi kung ito yung nucleus mo, the force that holds your nucleons together are very strong. Ay yung electron mo nandyan lang, paikot-ikot lang siya. So, it's much easier to get those electrons out than to go deep inside the nucleus. That's why when we already deal with nuclear energy, we are talking about very, very large amount of energy. Because that's what it can give you and that's what you need to do in order to manipulate a certain atom. So let's go to the third part of this video, your nuclear equations. So most nuclei in nature are stable and remain intact indefinitely. Radionuclides, however, are unstable and spontaneously emit particles and electromagnetic radiation. Emission of radiation is one of the ways in which an unstable nucleus is transformed into a more stable one that has less energy. The emitted radiation is the carrier of the excess energy. So parang what it says here is, through nuclear reactions, if you have a radionuclide or a radioactive element, of course, it will do everything in its power to reach stability. Kasi napaka-unstable niya, kaya siya nagre-release po ng energy para maabot niya yung kanyang stable configuration. And in doing so, pag nagre-release siya ng energy, that's what we call your radioactivity or your radioactive energy. So, if we talk about your nuclear reaction, it's very important to know the types of radioactive decay. Diba? As I said in the previous slide, a radioactive element will do everything in its power to reach stability. And upon doing so, mag-emit siya ng radiation through a series of different types of decay. So, pwedeng ito, kunyari meron akong isang radioactive element, gusto niyang ma-reach yung stability niya, and it can only do that by going through alpha decay, or beta decay, or gamma decay, or positron emission, or electron capture. So, different, depende po sa kanyang pangailangan, ang isang radioactive element po ay mag-undergo ng different types of decay to reach stability. And that is what we will be talking about in your nuclear reactions. So, let's first go to the first type of your radioactive decay, which is your alpha particle emission. So, that's the symbol for alpha. Alpha particle is emitted, or your alpha particle is also equal to your helium nuclei, which can be stopped by a vapor. So, medyo hindi pa masyadong, kumbaga, hindi pa masyadong delikado itong alpha particle emission. So, if this is your parent nuclei, di ba, parang ganyan siya, of course, that's your element, that's your mass number, and this is your atomic number, it will undergo alpha particle emission. Meaning, mag-emit siya ng isang helium nuclei. So, this is the alpha particle or your helium nuclei. Tapos, syempre, since natanggalan po siya ng dalawang proton, mababago na po yung element. So, that's how some of your radioactive element reach their stability by emitting an alpha particle. So, let's take a look at an example of an alpha particle emission. So, you have here an alpha particle emission. For example, you have your uranium having an atomic number of 92 and a mass number of 238. So, gusto niyang ma-reach yung stability niya, undergoing your alpha decay or alpha particle emission. So, pag si uranium-238 nag-undergo ng alpha particle emission, of course, mag-emit siya ng helium atom or ng alpha particle. Sometimes kasi in nuclear reaction, you will see helium or you will see alpha. Nevertheless, they are the same. Such that, pag si uranium-238, it actually emitted an alpha particle, what is the new element form? In this case, it's your thorium-234. This is actually very easy class kasi parang ano lang siya, addition and subtraction lang siya. So, 'di ba? Parang kung nag-emit siya ng alpha particle, alam mo na helium nuclei yung nandun sa kabila. So, that's having a mass number of 4 and atomic number of 2. So, ano yung bagong element na na-form? Parang ganito lang siya. 238 is equal to 4. Tapos, i-fill out mo na lang yun nasa gitna. Such that 4 plus 234 equals 238. Diba? Parang ganun lang siya kadali. Tapos sa baba, ganun din. So, you have 2. Tapos 92 dito. Of course, dapat dito 90. Para 90 plus 2 equals 92. And in your periodic table of element, you just determine which particular element contains the atomic number 90. And if you try to look back, balik tayo, para makita nyo. Ayun, thorium. Diba? You have it there. Thorium, 90. So, parang from your uranium, ay nakikita pala dito. Uranium 92, pag ang isang uranium nag-emit po ng alpha particle, magiging thorium siya. Thorium. Here. So, that's your alpha particle emission. Next one is your beta particle emission. So, when we say beta particle emission, it has this symbol, yung beta symbol. Beta particle is emitted or stream of high-speed electrons by an unstable nucleus which can be stopped by aluminum or other sheet of metals but cannot penetrate the skin. So, kumbaga, kung ito po yung parent nuclide mo, ito yung parent atom mo, maglalabas siya ng beta particle or an electron. So, electron po yung kanyang i-emit. Such that, if this is the electron, i-determine mo lang po yung daughter, parang yung kanyang magiging daughter nung parent. This is an example. So, you have your thorium 234, again. Diba kanina, uranium, ngayon thorium naman. Thorium 234 undergoing beta particle emission. So, ibig sabihin, may isang electron na may emit such that your electron actually has a mass number of 0 and a charge of negative 1. So, you just fill in the blanks. So, 234 is equal to 0 plus 234. Or dito, 234 plus 0 equals 234. And then dito, of course, 91 plus a negative 1 equals 90. And if you take a look at the periodic table, an element having the atomic number of 91 is your Pa, or if I'm not mistaken, that's palladium. So, madali lang naman siya. Parang ganun lang. Add and subtract. 91 plus a negative 1 is equal to 90. Tapos 234 plus 0 equals 234. So that's your beta particle emission. Next, let's go to your gamma radiation. Gamma has this symbol, yung parang Y na medyo maarte. So your gamma rays consists of high electromagnetic radiation of very short wavelengths. And this results from an energy release from the change of nucleus in an excited state to a more stable state. Kumbaga, parang yung inyong nuclide, nasa excited state siya. Therefore, to reach stability, parang kailangan niyang mag-emit ng gamma radiation to reach your stable nucleus. So, let's take a look at an example. So you have here your iodine 125 having an atomic number of 53 and a mass number of 125. It emits a gamma, your gamma rays to reach stability. As you can see, your gamma rays, it doesn't have any charge. So wala din siyang katawag dito, wala siyang charge, and then wala din pagbabago sa mass number niya. Kumbaga, parang ano lang siya. What happens inside is the nucleus is parang rearrangement lang po of your nucleons. Kumbaga, parang para ma-reach niya yung stability, kailangan i-rearrange niya lang kung ano yung nandun na sa loob. Parang gano'n. Such that, usually pag unstable yung isang nucleus, may makikita kayong parang asterisk. Para daw, pag nag-emit na ng gamma radiation, yung nuclide na yon, it will just reach its stable state. Just a rearrangement of your nucleons. Parang, so ganyan lang po yung kanyang nuclear equation. Sometimes the charges are written for your gamma, sometimes they are not. But either way, both are acceptable. Next is your positron emission. So particle that has the same mass as electron but an opposite sign. So positron emission. So, yung positron emission, it's like a beta particle. However, your beta particle kasi, di ba, contains a negative charge, and your positron emission is parang a beta particle which contains a positive charge. So, if you take a look at the sample equation here, you have your K, potassium, undergoing positron emission, and knowing that a positron is just an electron with a positive charge, ganyan po yung sulat, or you can do the beta or the E, it doesn't matter, it's the same. Such that if we try to identify the new element, di ba parang ganun ulit, 40 plus 0 equals 40, and 18 plus 1 equals 19. Such that if you take a look at the periodic table, the element number 18 is your argon. Paki-check na lang. I'm not sure if this is correct, but I think it is argon. So the last type of your radioactive decay is your electron capture. So electron captured by the nucleus of an electron from the electron cloud surrounding the nucleus. Diba parang dun po kasi dun sa loob ng, diba? This is your nucleus, it's surrounded by electrons. Tapos ang gagawin ni nucleus sa loob, parang i-attract niya or ka-capture niya yung isang electron. So that's why it's called your electron capture. So you have here an example of an electron capture equation. So you have your rubidium-82, which undergoes electron capture, and an electron or a beta particle contains a negative sign, which in turn will give out this element, such that 37 plus a negative 1 is 36, 82 plus 0 is 82. So you have your krypton 82. Sometimes this is the point of confusion. Ma'am, ano bang pagkakaiba ng electron capture sa beta particle emission? So when we say beta particle emission, yung element nag-emit siya ng beta particle. Kaya kung if you take a look, during beta particle emission, yung beta particle nyo nandito po sa product side. But during the electron capture, the beta particle is in the reactant side. Kasi kinapture siya nung element. So that's the difference between the two. So let's answer a sample problem on your nuclear equation. So it says here, the reaction of an alpha particle with magnesium produces a positron and a nuclide of another element. Now we are to identify the nuclide that was produced. So of course you are given, it says in the problem, you have your magnesium 25 and an alpha particle as your reactants. A positron is part of a product. Now you are required to identify the nuclide of the new element produced. So your solution, of course, is to write first the nuclear equation. So it says here, you have magnesium 25 and it will react with an alpha particle. And it will produce a positron, which is just a beta particle with a positive charge, and a nuclide of another element, which we represent as your X. Now, simply, as we have been doing, you just add the mass number of the products, and it should be equal to the mass number of the reactants. And you have to add the atomic number of the reactants and equate it to the mass atomic number of the product. So parang magiging ganito siya. So you have there 25 plus 4 is equal to 29. So dapat 29 din yung nasa kabila. So that's 29 plus 0. So ganun din, 12 plus 2 equals 14. So dapat yung nasa kabila, 14. May 1 ka na dito. So dapat, mali, dapat 13 to. Sorry class. So, dapat 13 yan. Such that, so, tama naman dito. So that, if you identify element number 13 in your periodic table, you will see it as your aluminum. So, the answer is this. You have your aluminum 29 as the product. So, let's go to the fourth topic, your patterns in nuclear stability. Now, we have already been talking about the different types of decay. Diba? You have your alpha, your beta, your electron, your positron emission, electron capture, gamma decay, and such. Paano ba natin malalaman? So, when we say patterns of nuclear stability, by using this, we can predict what particular decay a certain nuclide will undergo. So, parang maprepredict natin, ito kasi ganito siya, kaya siya mag-undergo ng beta decay. Or, ito ganito siya, kaya siya magkakaroon ng, or kaya siya mag-undergo ng positron emission, kaya ng electron capture. The patterns in nuclear stability will tell us that. So, how do we know what pattern to follow? You have your neutron to proton ratio. This is very important. The neutron to proton ratio, or commonly referred to as your N over P. Diba? By knowing this, we could actually kind of predict what decay a particular radionuclide will undergo. So it says here, the neutron to proton ratio determines the stability of a nuclide. Because like charges repel each other, it may seem surprising that a large number of protons can reside within the small volume of the nucleus. Diba, syempre alam natin na yung nandun lang sa nucleus are your neutron and proton. Yung neutron, 0 ang charge. So, yung proton, lahat yan puro positive charge. So, it's very difficult to hold all positively charged particles together kasi nga like charges repel each other. Kumbaga, kung pareho silang positive, parang tas ang dami-dami na nilang positive na nandun sa inyong nucleus. Parang it's very difficult na para sa kanila na to be closer together kasi i-repel na nila yung isa't isa. So it says here, at close distances, however, a strong nuclear force of attraction called the nuclear force exists between the nucleons. So kahit po kasi pare-pareho ng charges yan, lahat sila positive charge, because of the nuclear force, kumbaga nako-contain pa rin siya. Pero not for long, di ba? Kaya po yung mga matataas na nating mga element, atomic number having high element tends to become unstable. Kasi yun nga po, yung charges po ng mga protons within the nucleus is too much for the nuclear force to handle. Kaya po sila nag-i-emit ng iba't ibang different particles para ma-reach po nila yung stability. So, patterns in nuclear stability again. Neutrons are intimately involved in this attractive force. All nuclei other than, okay, disregard that statement. Mukhang incomplete siya. So, it says here, as the number of protons in a nucleus increases, there is an ever greater need for neutrons to counteract the proton-proton repulsion. So, ito naman na in-explain ko kanina. Pag masyado na maraming protons, parang mas malaki yung nuclear force na kailangan. So, sometimes hindi na kaya naghihiwalay po yung mga, or nai-emit po yung mga protons. Stable nuclei with atomic numbers up to about 20 have approximately equal number of neutrons and protons. For nuclei with atomic number above 20, the number of the neutrons exceeds the number of protons. Indeed, the number of neutrons necessary to create a stable nucleus increases more rapidly than the number of protons. Explain ko to mamaya when we go to the next slide. So it says here, thus, the neutron-to-proton ratios of stable nuclei increase with increasing atomic number. As illustrated by the most common of isotopes, you have your carbon-12. Now, parang ang sinasabi po, for a certain nuclide, radionuclide, to reach stability, dapat yung kanyang number of protons and kanyang number of neutrons are equal. So, parang yun po yung ideal. Or kung hindi man equal, it's very close to 1. Parang ganun. Para po maging stable siya. So, some of the most stable nuclide are given in the examples here. You have your carbon-12, which has, yung number ng neutrons niya is 6, and the number of protons is 6. You also have your manganese, which is a stable nuclide as well, having a number of neutron equal to 25, and of course the number of proton equal to 25, and the number of neutron to be around 30, such that if you get the ratio, it's 1.2. And you also have gold, which is the ratio is equal to 1.49. Pag titignan nyo naman tong sa gold, medyo malayo na siya sa 5. Pero dito nga siya nagpo-fall. If you take a look at this particular table, we call this the belt of stability. Ito po yung linear line. So, ibig sabihin yan yung 1:1 ratio. Pero ito po yung belt stability. Yung pinaka-dark na spots po, yan po yung belt of stability. Ibig sabihin, pag mas malapit po dyan sa inyong darker dots na yan, mas stable po yung inyong nuclide. So, it's not really linear. Parang meron siyang, diretso pa rin siya, pero hindi siya 1:1. Parang dito, malapit siya sa 1:1, pero pag pumunta na siya doon, pataas, medyo hindi na siya malapit sa number na 1. Although it's still stable. That's why we call this your belt of stability. Those dark, yung pinaka-dark na lines, di ba? Pag nandyan, stable, pag yung pinaka-dark. Yan po yung ating nagiging reference. How do you use this particular table? That's what we will be talking about in the next slide. The region of the graph covered by these darkest dots is known as your belt stability. I already mentioned that earlier. The belt of stability ends at element 83. So, element 83, somewhere there, 83, dito. Diyan daw nag-end yung belt stability, which means that anything above are radioactive. So here, the type of radioactive decay that a particular radionuclide undergoes depends largely on how its neutron to proton ratio compares with those of nearby nuclei that lie within the belt of stability. We can envision three general situations. So the first one is if we have a high neutron to proton ratio. The next one is the low neutron to proton ratio. And the last one is your nuclei with atomic number larger than 82. So ibig sabihin po, pag high yung kanyang neutron to proton ratio, nandito siya, dito po siya sa side na to. Diba? Above the belt of stability. If the neutron to proton ratio is low, nandito po siya sa baba. So that's the belt of stability. And special cases are those, those radionuclides having an atomic number greater than 82. So let's go through each one of these. So it says here, the first one, nuclei above the belt of stability, high neutron to proton ratio. So yung mga nandito. These neutron-rich nuclei can lower their ratio and thereby move toward the belt of stability by emitting a beta particle, because beta emission decreases the number of neutrons and increases the number of protons. So, ibig sabihin po kasi, pag high, pag mataas yung inyong neutron to proton ratio, masyadong maraming neutrons. So, therefore, para mabawasan yung neutrons na yan, dapat po mag-undergo siya ng beta particle emission. Such that, pag nag-undergo yung element ng beta particle emission, mababawasan po yung kanyang neutron. Mas lalapit siya dito sa belt of stability. The next one is your nuclei below the belt of stability. So, this region, dito banda. Which means you have a low neutron to proton ratio. So, this one naman, masyadong marami namang protons. So, kung yung kanina, pag nasa above of belt stability, maraming neutrons, dito sa below the belt of stability, marami po tayong proton. So, in order for your nuclei to reduce its number of protons, kailangan po siyang mag-undergo ng electron capture or positron emission. So, this one. Positron emission is more common among lighter molecule. Electron capture becomes increasingly common as the nuclear charge increases. So, either of the two, maaaring positron emission or electron capture, yung pagdadaanan po ng ating nuclei para lumapit siya dun sa belt of stability pag mataas masyado yung number of protons niya. So the third one is your nuclei with atomic numbers above 83. So these heavy nuclei tend to undergo alpha emission, which increases both the number of neutrons and the number of protons by 2, moving the nucleus diagonally toward the belt of stability. So, dito po siya. Pag above 83 na yan, mag-undergo po yan ng alpha emission. However, there's still a case na kahit above number 83 yan, mag-undergo pa rin siya ng tawag dito ng either beta or positron emission. Depende po sa kung ano yung magiging way para mas lumapit siya dun sa belt of stability. Pero yun, that's for higher, that's for masteral subjects already. So for now, these are the three generalizations that you would need them to understand. High neutron to proton ratio, meaning it will undergo beta emission. Low neutron to proton ratio, meaning it will undergo either positron emission or electron capture. And your nuclei with atomic numbers above 83 will undergo alpha emission. So, yun lang po for now yung kailangan nyong malaman. So, let's go now to the 1, 2, 3, 4 of fifth topic, your radioactive series. So it says here, some nuclei cannot gain stability by single emission. Consequently, alpha series of successive emissions occurs as shown for uranium-238 in the figure. Decay continues until stable nucleus, which in this case is lead-206, is formed. So one thing you have to understand about radionuclides are hindi pwedeng, sige gusto ko maging stable, mag-undergo kang alpha emission, tas okay na. It actually takes time and a lot of different types of decay in order for it to get its stable configuration. This is shown by your uranium-238. So this is your uranium-238. So let me explain this graph to you. Pag ganyan, the purple line will indicate that it underwent alpha decay rather, and the green line means that it undergoes your beta decay. So, ibig sabihin, si uranium-238, para maging stable siya, kailangan maabot niya si lead-206. So, dito po si lead-206. So, lead-206, uranium-238. Hindi naman pwedeng from lead-206 direct, or rather from uranium-238, magiging lead-206 siya. So, it should follow a series of steps para maabot niya yung stable configuration na yun. And those particular steps are what we call is what we call your radioactive series. So, pag nakita nyo dito, to interpret this graph, you have your uranium-238, tapos nag-undergo siya ng alpha decay para magiging ganito siya, which is your thorium-234. So, from thorium-234, mag-undergo siya ng beta decay, and it will become your palladium-234. Tapos beta decay ulit, your uranium-234. Tapos magiging alpha decay, alpha decay, alpha decay, alpha decay, alpha decay, beta, beta, alpha, beta, beta, alpha, hanggang sa maabot niya po si lead-206. And when your lead-206 is formed, stable na po siya. So this is your radioactive series. So it says here, a series of nuclear reactions that begins with an unstable nucleus and terminates with a stable one is known as your radioactive series, or sometimes, it's actually referred to as your nuclear disintegration series. So, in-explain ko naman na yan kanina. So, nuclear transmutation. So, it says here, thus far, we have examined nuclear reactions in which a nucleus decays spontaneously. So, we have been talking about how a nucleus or a nuclide decays. However, the nucleus can also change its identity by transmutation. So, it says here, if that particular nucleus is struck by a neutron or by another nucleus, nuclear reactions induced in this way are known as your nuclear transmutation. So, parang ito po yung ating particle. Tapos, we will be striking it with either an alpha particle or a nucleus or whatever, ganyan. Pag in-struck natin siya, of course, ito kasi parang mag-join siya. I-join niya dito mag-join siya. Such that, may mag-form tayong bagong element. Which is very true for the next slide, as Mr. Ernest Rutherford already performed this experiment. So in 1919, Ernest Rutherford performed the first conversion of one nucleus into another using alpha particles emitted by radium to convert nitrogen into oxygen. So as you can see, you have your nitrogen-14, and it was bombarded by an alpha particle, producing your oxygen-17 plus your hydrogen. So, from nitrogen, naging oxygen siya. So, diba, it's actually pretty amazing that you get to convert one particular element into a more helpful element. So, it says here, such reactions have allowed scientists to synthesize hundreds of radioisotopes in the laboratory. However, what is the catch? Diba? Parang it's amazing na, okay na, hindi na tayo maubusan ng oxygen sa mundo kasi kaya naman natin siyang i-transmute. However, the thing kasi about nuclear transmutation, it requires a very, very large amount of energy to perform. So, ibig sabihin, for Mr. Ernest Rutherford to perform this particular nuclear transmutation, not only it is very dangerous, but it required a very large amount of energy. That's why, sa ngayon kasi, hindi pa siya masyadong practical gawin because nga of the vast amount of energy that you need. However, maybe in the near future, parang pag wala na siguro tayong choice, parang maybe we could find a way to perform this nuclear transmutation without requiring a very, very large amount of energy. So going to the next slide, we start with your rates of radioactive decay or your half-life. Rates of radioactive decay or your half-life. So it says here, some radioisotopes such as uranium-238 are found in nature even though they are not stable. Other radioisotopes do not exist in nature but can be synthesized in nuclear reactions. So alam na natin itong mga to. To understand this distinction, we must realize that different nuclei undergoes radioactive decay at different rates. So, di ba? Ang dami nyo nang natutunan. So, alam na natin, we could actually predict by using the patterns in nuclear stability what particular decay a certain element will undergo. However, for the rates of radioactive decay, we are to determine gaano ba siya katagal magde-decay or gaano ba siya kabilis magde-decay. Depende po dun sa nature ng ating radionuclide or yung ating mga radioisotopes. So, many radioisotopes decay essentially completely in a matter of seconds. So, yung iba, parang halos hindi nga natin makita kasi 0.16, ganyan. 0.16 of a second, okay na siya, naging stable na siya. However, uranium-238, on the other hand, decays very slowly. Therefore, despite its instability, we can still observe what remains from this formation in the early history of the universe. So, yeah. The number of atoms of a radioactive element that disintegrate per unit time is a constant fraction of the total number of atoms present. The time required for 1/2 of the atoms in a sample to decay is called its half-life. So, half-life is very important. Kumbaga, half-life will tell you parang gaano ba katagal para sa isang particular radionuclei para maging kalahati na lang siya. So, kunyari, we started with 1 gram. So, gaano ba katagal para maging 0.5 grams siya? Parang gano'n. Or 10 grams. Gaano ba tagal para maging 1 gram na, or 5 grams na lang siya? Half-life will determine that. The half-lives of radioactive nuclides vary widely. For example, the half-life of your cesium-142 is 5 times 10 raised to 15 years. So, napakatagal po para sa cesium-142 para mag-decay. That of your radon-226 is 1,590 years. That radium yata to. Yeah. That of radium is 1,590 years. That of radon is 226. Radon-226 is 3.82 days. And that of polonium-216 is only 0.16 of a second. So, iba-iba po yung half-life ng iba't ibang elements. Some are faster than others. Radioactive decay is a first-order process. So, a first-order process, parang pag-aaralan nyo to, I think, sa calculus. The relationship between the initial amount of a radioactive isotope and the amount remaining after a given period of time is expressed by the logarithmic relationship that applies to all other first-order reactions. So, you have this particular equation that you have to know by heart. Diba? You have the ln of your n sub t all over your n sub 0 is equal to negative kt, where your n sub o is the initial amount, your k is your disintegration constant, Your N sub t is the amount remaining, and of course, your t is your time. So we will be using this equation in order for us to calculate your half-lives. So let's have a sample problem. It says here, calculate the percentage of a sample of cobalt-60, an isotope used in cancer therapy, that is left after 15 years. If your cobalt-60 has a half-life of 5.2 years. So using your GRS method, let's write your given. Of course, you have your cobalt-60 as your nuclide or your radionuclide, and the time for us, the time is given for us is 15 years. The half-life is 5.2 years. And we are required to calculate for the percentage that remains after 15 years. So, gano'n daw kadami yung may iwan after 15 years. So, for the solution, of course, how do you calculate the percentage that remains? That's simply the N sub t all over N sub O times 1,000, or rather 100%. And this is the main equation of your half-life. Again, you have your lone N sub t all over N sub O is equal to negative Kp. Now, of course, for us to be able then to calculate the percentage remaining, we have to assume an initial amount if it's not given. Anyway, since we are talking about percentage, kahit anong i-assume mo na initial amount, hindi magbabago yung percentage. Kasi percentage nga siya. So, for this particular problem, we will be assuming 10 grams of the initial amount. Okay? 10 grams ng initial amount, tapos if you want to do it on your own later, you can actually assume 100 or 50 or 15, and you will be able then to come up with the same answer as we will later on. And please take note of this. If your disintegration constant is not given, it is the very first thing that you need to solve. So, diba dito sa problem na to, we are not given the disintegration constant. So, therefore, you have to solve it first. So, solving for K, we have to manipulate the main equation, and it will give us this. So, ni-rearrange ko lang po yung equation such that we will be left with K on the right side of the equation, and you have your other variables on the left side of the equation, such that your disintegration constant is equal to the ln of N sub t all over N sub O, and that whole quantity is divided by the negative time. Remember that at the half-life of 5.2 years, diba? Kasi given tayo ng half-life of 5.2 years, only 50% of the original amount remains. So, ibig sabihin, pag nag-assume tayo ng N sub O na equal to 10 grams, after 5.2 years, ilan na lang ang natira? Ito yung kalahati ng 10, which is 5. That way, we could actually calculate for the disintegration constant. So that will be the ln of 5 grams, which is your N sub t, divided by 10 grams, which is your N sub O, divided by the negative time, which is in this case your half-life. So 5 grams na lang yung natira dun sa 10 grams after 5.2 years. Para ma-solve po natin si disintegration constant. Kasi po, yung disintegration constant, hindi po yan nagbabago. So, no matter, magbago man po itong mga variables na to, your N sub O, N sub T, your time, yung disintegration constant, it will not change because it is a constant. Such that, if we try to solve for this, you will come up with this answer. You have 0.133297534 per year. I-recalculate nyo na lang and make the necessary adjustment just in case that I'm wrong. So that's your disintegration constant. Now, going back to the main equation, We have to solve for the n sub t if the time is equal to 15 years. So ito ulit, i-manipulate natin yung equation such that yung n sub t na lang yung matitira dun sa left side and your other variables are on the right side. Doing that, you will come up with this particular equation. Dapat marunong na kayong mag-manipulate ng equation ha, na ituro naman na yun sa high school. So this is the equation and meron na tayong n sub o. This is the constant E raised to your negative disintegration constant in your time. So, filling it out, since you already have your NO to be equal to 10 grams, your E raised to the K, which we solved earlier, and the time, which is given to be 15 years. Here, isusulat po lahat dun sa disintegration constant. You have to write everything kasi we are dealing with very small numbers, and if you try to round it off or round it up, medyo malaki-laki po yung difference na mangyayari. So, for just for this, for our nuclear chemistry discussion, no rounding off. Such that if we try to calculate that, we will come up with an answer which is equal to 1.3541 grams. So, ibig sabihin, after 15 years, ang natira po doon sa 10 grams or na original amount natin is only 1.3541 grams. And by knowing that, we could already solve for the percentage that remains. Going back to the main equation, so i-fill out lang natin yung n sub t tsaka n sub 0. 1.3541 grams divided by 10 grams times 100% will actually provide you the percentage remaining, which is equivalent to 13.54%. So, yan po. And you can actually try solving the same problem using 1 gram or kahit 100 grams. And you should be able then to get the same answer. So now that we have talked about the rates of radioactive decay, we go to our next topic, which is energy changes in nuclear reactions. Energy changes in nuclear reactions, dito na po natin isosolve kung gaano ba kadami yung na-release na energy or yung kailangang energy ng isang nuclear reaction. The energy changes in nuclear reactions is associated with your Einstein equation. So, madali lang siya. Yan lang po yung equation. E is equal to mc squared, where E is your energy, which is, as you have been noticing, we are solving it using the main unit, which is joules. And then your M will stands for mass change, which is in kilograms. And your constant C is the speed of light. So, constant naman yung C, which is 2.9979 times 10 raised to 8 meter per second. So, madali lang siya kasi yan lang. O, dalawang variables nga lang yung E tsaka yung M lang. Or rather, yung isa na nga lang yung M lang po, yung mass change. However, kasi the calculation of the mass change is very different. So, it's very critical that you know how to calculate the mass change kasi pag hindi mo alam kung paano i-calculate yan, o di mali yung energy na masosolve mo. So, let's have a sample problem. It says here, how much energy is lost or gained when 1 mole of cobalt-60 undergoes beta decay? The mass of your cobalt atom is 59.933819 atomic mass unit, and that of nickel atom is 59.930788 atomic mass unit. So of course, as we have been doing before, we do your GRS method. So we are given 1 mole of cobalt-60. We are given the mass of the cobalt atom, which is those numbers, and you are also given the mass of your nickel atom. Now we are required to calculate for the energy. So, energy changes in nuclear reaction. This is the solution. You have that main equation is equal to mc squared. Now, of course, the first thing that you need to do is to write the nuclear reaction involved. Si cobalt-60 daw, naging nickel-60. And, paano siya naging nickel-60? If we try to fill out the blanks there, nag-emit siya ng isang beta particle. So, such that, diba, 60 plus 0 is equal to 60. 28 plus negative 1 is 27. So, meron ka ng speed of light, which is, diba, given as a constant. Yung mass na lang naman ang problema para makalculate natin yung energy. So, calculate the mass difference. How do you calculate the mass difference? It's simply the mass of the products minus the mass of your reactants. In this case, the mass difference, which we will just be abbreviating as M, is equal to the mass of your beta particle plus the mass of your nickel nuclide minus the mass of your cobalt. And if you take a look, you have the note here. You have to make sure, sorry, that's typographical error. You have to make sure to consider the mass of the nucleus only. Diba, if you take a look, you are given the mass of the atom. And in the atom, you have your electron, your proton, and your neutron. Since we are talking about nuclear reactions, you have to consider the mass of the nucleus only. So, ibig sabihin, dun sa mass ng atom na yan, kailangan natin ibawas yung mass ng mga electrons. So, the mass of a beta particle, please take note of this, it's 0.0055 atomic mass unit. Yan po yung kanyang weight. I think nabigay ko to dun sa mga previous slide. If you take a look dun sa introduction. I was able then to provide the mass of the proton, the mass of the electron, and the mass of the neutron. So, mass of your beta particle or your electron is 0.00055 atomic mass unit. The mass of your cobalt-60 nucleus is the mass of the cobalt-60 atom minus the mass of the electrons in the cobalt-60 atom. So again, yung mass ng atom minus the mass of the electrons inside that atom para makuha natin yung mass of the nucleus. And how do we calculate for that? The mass of the cobalt-60 nucleus is equal to 59.933819 atomic mass unit. That's the mass of the cobalt atom minus 27 times 0.00055 atomic mass unit. Bakit po 27? Kasi if you go back, let me go back. Diba we mentioned earlier that the atom is a neutral particle. So, ibig sabihin, kung ano po yung number ng protons, kasi positively charged yun, ganun din po yung number of electrons. For you to have a stable atom. So, ibig sabihin, kung 27 po yung number of protons, 27 din po yung number ng electrons doon sa ating atom. And each electron will actually weigh 0.00055 atomic mass unit. Kaya ganyan po. 59.933819 minus 27 multiplied by 0.00055 atomic mass unit. Para yung makuha na lang natin is yung mass nung mismong nucleus, which is 59.918969. So, yan na po yung mass of your cobalt nucleus. We will be doing the same thing with the mass of the nickel nucleus. So, kailangan yung mass lang din ng nickel na nucleus yung kukunin natin. So, performing the same process, but however, for your nucleus or your nickel nucleus, it has 28 electrons. Such that you will be calculating this particular number, 59.915388 atomic mass unit. So, going back now in calculating the mass difference, mass of products minus mass of reactants, tapos ito equation, the mass of your beta particle plus your nickel minus the mass of your cobalt nucleus, okay, is this one. So, your 0.0055 atomic mass unit plus 59.915388 atomic mass unit minus 59.918969 atomic mass unit. And it will give you the mass difference equal to negative 3.031 times 10 raised to the negative 3 atomic mass unit. Now, one thing that you have to remember is that when you get a negative mass, it entails that the reaction is exothermic, meaning there was a release of energy. And of course, diba, as one of the requirements of the Einstein equation, your mass should be in kilograms. So this is in atomic mass unit. So how do we convert your atomic mass unit into kilograms? We actually have a conversion factor, which is given as this one. So for you to convert one atomic mass unit to kilograms, you have this one. So, ang dami nyo na kayo. Ito kailangan nyo memorize to kasi I think this is the new conversion factor to you. Such that your negative 3.031 times 10 raised to the negative 3 atomic mass unit is equivalent or multiplied by rather 1.661 times 10 raised to the negative 21 kilograms per atomic mass unit. This atomic mass unit and this atomic mass unit will cancel with each other, leaving you a mass equivalent to negative 5.034491 times 10 raised to the negative 24 kilograms. So, yan na po. Yung mass difference. So, diba? Yung mass lang naman yung problema nyo. However, it's very critical that you know how to calculate the correct mass. Now, since meron na tayong mass, we could already calculate for the energy. So, going back to our Einstein equation and filling in yung mga meron na tayo, you have the mass, you have the speed of light, you will be given this equation, di ba? Negative 5.034491 times 10 raised to the negative 24 kilograms multiplied by the speed of light, which is 2.9979 times 10 raised to 8 meter per second, the whole quantity squared, to give you an amount equal to negative 4.524700662 times 10 raised to the negative 7 joules, and this is in terms of per nucleus of the cobalt atom. So, yung nasolve nyo dito, isang nucleus yan per nucleus of the cobalt atom. Siyempre, as with the requirement of your Einstein equation, dapat joules lang yan. So, how do we get rid of this nucleus? This is the point where we actually use your Avogadro's number. So, solve the energy in terms of kilojoules or joules. Tingnan natin. So, you have here, diba? You have that particular number, joules per nucleus, and you have your Avogadro's number, which means that there are 6.022 times 10 raised to the negative 23 nucleus per mole. Ibig sabihin, ganyan po yung karaming entity per mole dun po sa nucleus, multiplied by 1 mole of your cobalt, kasi given tayo ng 1 mole of cobalt, para po makancel natin yung nucleus na yan. Parang ganito ibig sabihin niya sa bawat nucleus, meron kang ganyang amount of energy. Sa bawat mole, ganito po kadami yung nucleus. And you are given 1 mole of cobalt, such that you can get rid now of the nucleus there and the nucleus here. And you can get rid of the mole here and the mole here to provide you this amount of energy. So you have negative 2.7248 times 10 raised to 17 joules of energy that was lost. Kasi exothermic po yung process. So ibig sabihin, pag yung cobalt nyo, cobalt 60 nyo, nag-undergo ng beta particle emission para maging nickel 60 siya, ganyan po kadaming energy yung inilalabas niya. Okay? So, there, that's how you calculate for the energy changes involved in nuclear reactions. So, I think, I'm sorry, it's too long, but this is a topic that's supposed to be talagang mahaba po siya. But hindi, wag na tayong, sorry, let me, i-edit ko yan. Wala na tayong quiz next meeting. For the next meeting, please be prepared for a synchronous meeting. So, live po tayo next meeting. That is for you to be able then to answer or to ask any questions that you may have before your midterm exam. So, please prepare your questions prior para po ma-address natin siya sa ating meeting on the next meeting, and kasi 40 minutes lang po yun. And also, after the synchronous meeting, I will be providing you the next topic, which is on fuels. No activity for this particular topic kasi po yung activity dito is ibibigay po sa laboratory. For you to be able then to practice calculating your nuclear energy changes. So I think that's it for me, class. I hope you enjoyed watching this video. I know that it's very tiring to watch it, but I want you to know na at least dito you could always replay it, or you could always repeat some things that you did not understand. Let me just tell you na this pandemic kasi, of course, it brought about a lot of changes that we need to adjust to, and one of which is you have to help yourselves. So I can only do much here on my part, but I also all I can say is you have to do your part as well. If what I'm providing, what I'm giving you is not enough, it's up to you to supplement. After all, you are already in college, so help yourselves, guys. So that's it for me. Stay home, stay healthy, and stay safe. Goodbye, class. Have a great day.